Okay, welcome to our ideal gas law PowerPoint here for gases. This is kind of our last stop. We're going to perv nerd. Yep. No, that means pressure times volume equals number of moles times a constant times a temperature. Oh, that's kind of weird. Maybe you recognize some things in there. Like we've been talking about pressure and volume, and PV equals PV, or PV1, P1 V1 equals P2 V2. So if you change the pressure and volume, but everything else stays constant, then they should equal a constant. Okay, so what we're saying is, if you know something about this, you should feel like if you know pressure and you know volume and you know how temperature actually, then you should be able to estimate how many moles of gas is in that container, as if you're assuming that all gases are acting the same, if they're ideal. Okay, which means they aren't attracted to each other at all, and the volume of the molecules of gas themselves doesn't really contribute to the volume. Okay, that the volume of the gases, generally speaking, is tiny enough compared to the volume of the space in between them, so that it doesn't really come into play. But that would be ideal. So ideal gas law. We talked about temperature, how temperature can be related. So maybe you don't recognize it in this form. It's nice because we can perv nert. Okay, maybe that's just one way you're gonna remember it, or not. But really, is this guy here, Avogadro. He not only he invented Avogadro's number. Okay, he decided that he wanted to know to make standard 1 gram of hydrogen particles. All right, hydrogen gas, really. 1 gram of hydrogen, yeah, particles, really. And he counted those, and it was 6.02 times 10 to the 23rd. That's a lot. That's more than trillions. Okay, obviously. And but he also did some work with gases, and he found out that equal volumes of gases contain about the same amount of particles, the same number of moles of particles of that gas, as long as the temperature and the pressure was kept constant. Okay, and this is pretty much true for any gas, give or take. All right, so we got the ideal gas law because of Avogadro, and it's pretty much the pressure, temperature, and volume relationship and a constant, but now we can throw in numbers of moles, so you could increase or decrease the number of moles, or you could estimate how many moles you have if you know all the other stuff. Okay, that's kind of weird. Well, here's a form of the equation that makes sense to me. All right, so we sure have pressure and volume together because they're inversely proportional, right? If you increase one, the other one wants to decrease. And then we have temperature on the bottom that kind of looks like half of your combined gas laws. All right, if you take away the moles and cover up the moles. But yeah, Avogadro basically said, yeah, you can not only does this equal a constant, but you can also factor in the number of moles of this gas, and then it's going to be a certain constant R. And for most gases, actually, you can kind of estimate that. The reason why is because at 1 atmosphere, and if you have 1 mole at 273 Kelvin, so that's 0 Celsius, and you have, I think it's 1 liter, then you're going to get this number. And then if you mess with it, it's the same. It's always going to equal the same constant. Kind of like how we could put the combined gas law together. We just didn't know what the constant was. Okay, I don't know if that's making any sense to you. But if you're using liters, atmospheres, moles, and Kelvin, then it's 0.0821. All right, as long as you know everything else. Oh, I'm sorry, I don't know why that did that. As long as you know everything else, then the pressure times volume divided by number of moles divided by temperature should equal that number. It says decameters or decimeters. Sorry, that's decimeters cubed times kilopascals times mole Kelvin. I believe decimeters cubed is just a liter. Okay, so yeah, we are just being funny here. So if you see anything in decimeters, a deci is 1/10 of a meter, but decimeters cubed, then that's a liter. Okay, so just think of it as a liter. So yeah, you can figure out if you know the pressure in kilopascals. That's just going to change this number because the units are a little bit different. But you got to always use Kelvin. And you got to always use moles. Okay, so we're assuming ideal gas law for a gas. We're going to idealize it. Okay, and we're going to perv nerd. All right, so keep that in mind. We're going to use that in a couple calculations. All right, so we're saying this time calculate the pressure in atmospheres. We have to use the right constant in atmospheres of this amount of moles, 0.412 moles of helium. Doesn't matter what it is because we're going to assume it's all the same. It's idealized. All right, love it. At 16 degrees Celsius, occupying 3.25 liters. Okay, we're okay in the liters, not okay in the Celsius, right? We got to use Kelvin because Kelvin's the scale where 0 temperature is 0 energy. All right, just like in the scale of volume, 0 liters is 0 volume, and 0 moles is 0. So we have to zero the zeros, yes. So let's do 273. Let's just add that. Oh goodness, that's interesting. Let's practice with our eraser here. All right, let's start over. Let's try this again. Oh, that's a highlighter. Nope, I want a pen. Okay. 16, and let's just add 273. Okay, so they kind of did that down here. It ends up being 289. All right, we don't know the atmospheres, so we can put an X for that or whatever. Oops, we don't know the pressure, but we want an atmospheres, so we're going to use the 0.0821 atmos because that's the one that's in atmospheres for the constant. Plug in your volume, plug in your number of moles. You're going to perv nerd. Okay, just put an X for one you don't know what it is, and then solve for the rest. Okay, so we got X times 3.25 liters. Maybe you want to try this first, and so you want to pause the video and then do your thing and then come back to it. Welcome back. Okay, so that's moles. That's 0.412 moles times R, running out of space. So I'm just gonna kind of like do that here. 0. Goodness, not sure how just likes to get all fancy on you. All right, times those points supposed to be 0.0821 times the temperature, which is 289. Okay, when I go too light, then it skips. Okay, this is fun. All right, so that's all times. So you and I both know you have to divide out the 3.25 liters, right? So you would take all this, multiply it, and then whatever that is, put over 3.25. So remember, that's how you do that cross multiplication thing. So yeah, clear as mud. Let's see how we did. Next slide. Here we go. All right. Much clearer when they have it typed out. Nice. And it's 3 atmospheres, approximately. 3.01. Yeah, we can do that because we have 3 significant figures in all of our measurements. We have 3 in the number of moles and in the number of liters. We didn't really in temperature, so I don't know if we can actually, unless it was 16.0 Celsius. Okay, then that would be 3 significant figures. Okay, remember, I'm not going to worry about significant figures. I just like mentioning it because, you know, it could be a thing in your future classes. All right, next problem. I love this because we like to idealize life with the ideal gas law. Okay, so we're not changing anything. Remember, we're just trying to find one thing about a gas if we know all the other stuff and we use the right constant, R value. Okay, so this time we don't know the volume, but we do know the number of moles. Oh, looks like we had to find out the number of moles. Look at here. 85 grams of O2 at 25 degrees Celsius. So you had to take the 85 grams, or you have to, and convert it to moles. Do you remember how many grams is 1 mole? Well, for oxygen, it's normally 16, but it's O2. So it's twice that because there's 2 oxygen atoms per oxygen molecule. And we're talking particles of oxygen. So we're not talking like individual number of atoms. We're saying 1 mole of oxygen gas. Okay, so it's going to weigh twice as much. So we're going to say, yeah, 32 grams. Okay, so you got to do that math. Get the moles. Apparently that's 2.7. All right, practice that so you get comfortable with that. All right, and then plug and chug, right? You're going to perv nert, so start with a P. 104.5, that's a 0. Okay, not an 8. KPA, I'm going to put the units at the bottom. That's better. Times the volume, we don't know, so that's times X. I'm throwing X over here, just, run out of space here. PV equals N. There's your moles. Times R. We just like to do R next because perv it doesn't sound right. You need perv nert. All right. So the R value that we're using, so we can do kilopascals, use kilopascals, is 8.315. Again, weird line stuff happening. Not sure. Times 298 Kelvin. Oh, that's right. We're supposed to put the units below. Oh, well. So the R value. Now, what I would do is write the units of the R value, which, by the way, that's liters, decimeters cubed, just being funny. Liters, kilopascals over moles, Kelvin, and then the units are going to cancel. If you put down the units of the R value, like the liters would cancel, liters would be on top, right? Because we're going to, well, I mean, not the liters. Yeah, like we're trying to find liters. My bad. Liters won't cancel. Liters will be left. Moles will be on bottom, and Kelvin would be on bottom. See how the moles on top cancels out moles on bottom. Kelvin on top cancels Kelvin on bottom. KPA would be on top, but you would divide each side by 104.5. KPA, K-pop. K-pop. That reminds me of K-pop. Just fun. 104.5. Okay, so the KPA would cancel out if you had KPA for this R value on top. Okay, making a mess of this. Yeah, this pen is interesting. Well, here it is all typed out and nice and orderly, and my picture's in the way here. That's not fair. So you did the conversion. They show the conversion here. Perv nerded. And then, yeah, maybe you can see that the K is on the bottom, so it'll cancel out the K on top. Moles here, moles there, cancels that. KPA, you would divide each side by 104.5 KPA. And you get 64 decimeters. Sure. It's okay. Take me to your leader. Yeah, nobody uses decimeters. Who does that? Okay, super perfect. Try the assignment and see what you can do, and then do the quiz, and let me know in the comments below what maybe what I need to focus on or something I messed up. It happens. Okay, so thanks a lot for coming along, and I hope you're having a good day. We'll see you.